So what have we learned so far? So we have defined our vectors, right? Let's have a brief review, then we'll start. So we defined our vectors. So and the vector like a vector, some v was defined was defined through a derivative of a point, actually a curve, with respect to its parameters. So it was like this, some lambda, where this curve is defined as like p of lambda, and the derivative would give you like this tangent vector, right? So using that, we defined the basis vectors as well. So instead of like arbitrary, like this lambda parameterization, if we have coordinates to parameterize the space, then we would have a set of basis vectors, namely E mu, where mu runs from 1 up to n, or 0 up to n minus 1, depending on your convention. So this is what we have, what we had actually previously. Yeah, and I'm putting this tilde over p always, because it's a multi-component object, but it's not linear. So any vector object, some w, can be written in terms of components and the basis. So in terms of basis, we can write it like that. Then we define something else. We defined the one form objects, right? One forms were defined to be like infinitesimal changes in some scalar quantities, say f, like that. This was like defining definition of alpha. Then we actually defined the corresponding basis, basis one forms. So those were like omega mu with the lower bar, because these are one forms. So it was like this. I believe everyone remembers this stuff, right? And then we saw the piercing of these things. That if we have an infinitesimal change in f, and if you want to like measure how much the f changes in total when you go through, like when you start from v and end up at the tip of the v, then what's the difference between f? That was your piercing of df and v, right? Basically the rate of change of f with respect to p, with respect to lambda. So we had like this. Oh, sorry, not like that. The opposite.
Yeah.
And using the definition of this piercing process, we defined, actually we were able to calculate some results. So the first result were like computing components. So if you want to component like component of v, or say w, so then w mu would be like omega mu pierced with the object vector w, right? Like that. Then if you want to for some one form beta, where beta one form is like these are the components, and then this is the basis. Then components of beta was like this. Beta pierced with inu, that would give you like this thing. And obviously from the definition of piercing, it's apparent that if we use like if you pierce omega mu to like inu, that would definitely give you omega delta. Then we these were the things that did not require any kind of metric tensor defined on the system, right? But there were few other operations on vector and one form. So we discussed in tensors in general, but we are actually right now we are actually picking only the only relation involving vector, one form, and metric tensor. So that's what right now I'm summarizing a little bit. So then the relation between a vector and its corresponding one form was like we usually write like v lower bar, which is defined as which is basically flat of vector v. Flat is an operation operated on this vector and defined as, how is it defined in terms of metric tensor? It's ds squared, which is the metric tensor of metric tensor, and you keep one of its slot empty and supply v in the second slot, like that. Now,
Yeah.
now again, when ds square was defined, we proved that g, which is kind of inverse of ds square, in components they are true, they are inverse of each other. So they have actually like the opposite action on this v object v and v bar, like that, v lower bar. So we also saw that for that object, you can actually find the corresponding vector of an arbitrary one form, say alpha. So the corresponding vector of an one form alpha is alpha upper bar, which is basically sharp of what? Alpha, right? And that is it's again the inverse metric tensor, and you have to supply alpha in one of its slot and keep the other slot empty, like that. What else did we learn? What else did we learn regarding this vector and one form? We learned their transformation property, and they come from this definition of basis. But what else? Did you learn anything else regarding this? Okay, can you prove this result? If you pierce v lower bar, which is a one form, with alpha upper bar, which is a vector of corresponding to, and that is equal to this thing. Can you prove this? If you want to prove it, how do you proceed? Any idea?
Maybe using the definition of flat and sharp? No?
Yes, yes, yes. Just directly use these definitions and substitute. So if you substitute, like from left hand side, you have flat of v, then alpha upper bar is sharp of alpha, right? And what's this thing? It's basically metric tensor filled with a vector v, and this thing is the inverse metric tensor fitted with alpha, like that. And then in if you expand this thing, we already seen that it can be expanded like this. G mu nu v nu e mu, right? Actually, so it's okay. So it's omega mu, like that. We have already seen that, right? So when we expanded this thing.
Yeah.
And what will be for the same like the result for this part? Sulaiman, can you tell me? Okay, Arafat.
Well, it will be G upper lambda nu or lambda rho.
Yeah, something new.
Uh,
Yes.
a lambda
Then
rho alpha. So we are actually sharpening it. So okay, so let's contract with lambda, alpha lambda, lower lambda,
yes,
and E rho.
right. Then this is just a number, right? This part is just a number. The only like one form object is this omega mu, and this part is also a number. The vector part is this e rho. So we can like pull those out of this angle bracket, right?
How did we consider those parameters lambda and other one?
Oh, okay. So one thing you have to remember that these are dummy indices. When you are contracting, that means they when they're summed over, it doesn't matter which index you use, but you have to be careful that you do not use the same index twice to sum over something. So see, we have all in this expression we have already used mu and mu to sum over, right? So
Yeah.
you could pick something else. You could put like sigma, then like G sigma rho, alpha sigma e rho, like that.
Okay.
But you cannot pick mu nu. Except for those, you can pick anything else.
Okay. And how do we know that we'll use that E bar row?
What do you
Like,
mean?
no, I mean, this is I'm clear. Like, I'm clear about ds square. We have already defined this, but I'm not clear how we got this G bar, and in this term, how we got this E row bar.
Oh, okay. We found the inverse relation for like ds square is something that can convert a vector to a one form, right?
Yeah.
So if ds square is so it's making a linear transformation from a vector to a one form, right? So if this linear transformation has to be unique, that means you put one unique vector and you get one unique alpha, then which it should be, otherwise like ds square is not well defined. So then obviously there should be a method to convert a one form, like the say you had your vector v and you convert it to, like, you do a flat on it, so it becomes like a one form, say beta. So now as this relation like um, v to beta is unique, there should be a way to come back from that, right? Go the other direction like this. So
Yeah.
that's the part. So this operation, the forward operation, like vector to one form, that's done by ds square.
Mm-hmm.
We demanded that the opposite transformation exists, so that automatically gives us like g. So So ds is, d is just the inverse one, inverse tensor of ds square.
Yeah.
So if you want to write in terms of components, then ds square is like g lower mu nu omega mu times omega nu, right? That's we know already.
Yeah. Mm-hmm.
So this thing, this g is defined as g say kappa lambda, then e kappa times e lambda, where we already saw that when we demand this thing, then this has to hold, like g mu nu, g nu lambda has to be equal to Kronecker delta mu lambda, which means if you consider a matrix out of these components and another matrix out of these components, those matrices will be inverses of each other. So basically, it means like whenever you have a ds square, so you can construct a matrix out of its components. You just find it in inverse. That will give you G.
Okay.
Is that clear?
Yeah. Now it's clear.
Okay, so we are getting this E row because it had like another say E lambda, and we are actually feeding that in that slot some alpha. So we are left with like G lambda rho, alpha lambda E rho.
Okay.
So this part, this curly brace part, these are just numbers. So we can pull out of this piercing process. So it'll give you like G mu nu V nu, then G lambda rho, alpha lambda, and then you'll have like omega mu E rho, like that. So what would be this what this piercing would be? Can you tell me, Prashanto? Can you tell me what's the result of this thing?
Kronecker delta mu rho.
It's a Kronecker delta mu rho. Okay, great. So now, if we proceed, then we can sum over this mu index. So if you sum over that, it will give you G rho nu V nu then G lambda rho alpha lambda, right?
Yeah.
So now see, we have a sum over two indices of G itself. So now you can write like this: G lambda rho, G rho nu, right? Then V nu alpha lambda.
Yeah.
So can anyone tell me what this part would be? Jaber, can you tell me? Okay, Humaira, can you tell me? Hello? Okay, if it's too hard, I think I can simplify it for you. So this matrix, like the matrix part, like the metric tensor, when it's written in component wise, if you construct a matrix out of it, then the matrices are symmetric, right? So in other words, metric tensors are symmetric means we can actually switch those indices without any problem. So we can write like this: right? And then we can again write like this. So now can you tell me like what this thing would be? Robin Roy? Can you tell me? Tell us what's this part going to be?
Delta mu lambda. No, oh, sorry, Kronecker delta mu lambda.
It's Kronecker delta?
Mu lambda.
It's nu lambda, right? Great. So we are having this, right? Now, if you again sum over this, any of those indices like either lambda or mu, you'll have finally this thing. Say we are summing over lambda. So you'll get phi nu alpha nu, which is we already knew from that's the result of piercing, right? That is basically the result of piercing of alpha as one forms and v as vector, right?
Yeah.
So we have already proved that this result is true. This result is true, right? Okay, so now let's talk about isomorphism. We have already learned it. Okay, isomorphism. So any idea what isomorphism could be? What it could mean? Any idea? Any idea what it could be? And have you ever heard this term before?
Yeah, I have heard, but I could not remember.
Okay. Okay, so it might not be like that much unknown to you. So iso means same, right? Iso means same. ISO means same. And morph, what does it mean?
Change?
Morph is shape. It means shape.
Okay.
So if two objects give same shape or same structure, we call it isomorphism between those two. So basically isomorphism we mean if we are representing same thing in two different ways, then we call it like that's isomorphism between this thing and that thing. See, like we have a one-to-one correspondence between a vector and a one form, right? When metric tensor is defined. So if we had a vector, we were able to find a corresponding one form using this flat process, right? Like under ds squared. And under G, we were able to find the corresponding vector to the one form beta under this process, obviously. So basically, here we are meaning like we were always able to find when metric tensor is defined, we were always able to find a corresponding one form to a vector and a corresponding vector to a one form, which means basically they are representing same thing but in different ways. So these objects like this flat and sharp, these two are known as musical isomorphism. It's an isomorphism, and these notations are taken from actually music, so that's why it's called musical isomorphism. We'll learn one more kind of isomorphism. That's later. So that will be our Hodge dual. So okay, is that terminology clear to you? So whenever you see musical isomorphism, they mean we are actually converting a vector to one form or one form to a vector.
Yes.
Okay, great. What were we learning last time, like when we ended the last class? What's the last thing we learned? What is the last thing we learned? It's just been 1 week, so everyone forgot already?
I
Sorry, I
think we
missed the
learned.
question.
Sorry?
I mean, I missed the question. Actually, what was the question?
Well, so what were we learning last time when we stopped the last class?
Oh,
Like, what is the last
uh,
topic we learned?
you addressed the operation exterior derivative and talk about the approaches.
Okay. So basically, we were learning like tensor operations, right? What can be done on a tensor. That's what we were learning.
Yeah, and I think you said we'll be starting with geometrical interpretation for P form, I think.
Yes, exactly. So yes, then we are in the good position to like start interpreting our P forms and P vectors. So let's review a little bit of wedge product, because we just learned it, but we haven't actually expanded on it. So let's expand on wedge product a little bit, then we'll start like doing the other part. So let's sharpen our like terminologies in P forms. So basically what we are learning here is box number 4.1, exterior algebra. So here we already have discussed, like we have our basis one forms and we can expand on one form in terms of the basis, right? So the basis one forms were like omega mu's, that were like dx mu, and we can actually write our some one form beta as like beta nu omega nu, right? That's we already have. Then we have its transformation rules, and we already know that. Let's not worry about that, because we are using in full form, so it's easily recognized which part is actually tensor, which is not. Okay, then the structure of a general P form. A general P form. So a P form should have P number of this one form object wedged together. That means if you have like alpha 1 is a one form, alpha 2 is a one form, and up to like alpha p. If you do this, alpha 1 wedge alpha 2 wedge alpha 3, like that, up to wedge alpha p, then the object you get is a P form. So it's an example of P form. It's not the absolute general one. Obviously, not all P form can be decomposed in terms of one forms, obviously. but there some can be like, okay, we'll explain that in a moment. Okay, so let's write in terms of some basis one forms. So if you have a P form, say let's call it beta. If beta is a P form, and if beta is a P form, then it should have basis like this. So beta should have a structure of this form. So considering the basis forms, like it will be like omega-1 wedge omega-2 up to P number. So you are expecting P1 form basis in beta. P1 form basis in beta. So let's start by writing a 2 form, then we'll understand what we are going. So a generic 2 form, say let's call it gamma. So gamma is a 2 form. If it's a 2 form, the basis, okay, it depends on the how many dimensions do we have, obviously. So let's say we have 4 dimension, 4D. In 4D, how many one forms can you write? How many independent one form can you write? Is my question clear? In 4 dimension, how many basis one form do you have? How many basis one forms do you have in 4 dimension?
Four basis one form.
Yes, 4 basis one forms. What are those?
We can just call them omega-1, omega-2, omega-3, and omega-4.
Yes, we can call them omega-1, omega-2. Okay, let's do it in 3 dimension. That would be like easier for everyone, I think. Like that. If it is in 3 dimension, then we'll have just 3. So now you can choose to make a 2 form. You can pick any 2 of these 3, right? So if you take like this first 2, you'll have like omega-1 wedge omega-2, like that. How many possibilities do you have? Like let's start having like you could choose same thing twice. So then you'll have like omega-1 wedge omega-1, then omega-1 wedge omega-2, then omega-1 wedge omega-3. So how many this kind of object, basis object, can you create out of it? Say we are doing in 3 dimension. You're choosing this omega-1, omega-2, and omega-3s.
9.
9.
Obviously. So let's write those things. Let's write those things. So omega 2 wedge omega-3 1, then omega 2 wedge omega-2, then omega-3 wedge omega-3. Sorry, not 2 wedge omega-3. That's okay. Then
Omega-3 was omega-1.
omega-1, right? Then
Omega-3 was omega-2.
omega-3 wedge omega-2. Then
Omega-3 was omega-3.
omega-3 wedge omega-3. Okay. Now we know how to take wedge product between 2 objects, right? Like 2 one form objects. We already defined. So with this definition, what omega 1 wedge omega 1 would be? Can you expand it? I'm just trying to show you the pattern. So that's why like we're doing this. Otherwise, I'll just define. I'll say the definition this and let's do math with it.
I think it will be 0.
How? So the definition of
Because,
omega 1 wedge omega 1 is, yeah, tell me.
omega 1 direct product omega 1 minus omega 1 direct product omega 1.
It's read as like not direct product times, like omega 1 times
Okay, omega 1 times
omega 1, then minus
omega 1 times omega 1.
omega 1 times omega 1. So you can see like when you take wedge product between same object, that gives you 0. So how many of these nine things will go away?
3.
3. Which one? This one already isn't there anymore now.
Yeah, diagonal elements 2 2 and 3 3.
Now let's evaluate omega 1 wedge omega 2. So how can I evaluate that? Actually, I cannot evaluate. It doesn't have a value, but we can actually expand in terms of direct products, right? Omega 1 times omega 2 minus omega 2 times omega 1, right? That's like what I can write. But if you're careful enough, you'll see that if you factor out one of that minus out of this whole thing, then we'll get omega 2 times omega 1 minus omega 1 times omega 2, right?
Yeah.
Can you recognize this thing?
Yeah. Omega 2 omega 1.
Yes. So inside of that square bracket, you have like omega 2 wedge omega 1, right? So you can see like omega 1 wedge omega 2 is negative of omega 2 wedge omega 1. So these two things are not independent. They are actually negative of each other, right?
Yeah.
Okay, then what else? On which of the things we can say the same thing? And can you show me more pairs like that?
Yeah. 2 3 3 2.
These two.
Yeah.
Right? And obviously these two. So in 3 dimension, for a one form, for a 2 form, you can have actually at most 3 independent things, right?
Yeah.
At most 3 independent bases. So we can write our beta, gamma, which is we claim to be a 2 form. So probably we can write it like this, because you can at most it can have 3 independent bases. So say gamma 1 omega 2 wedge omega 3, that's an independent one, right? That's non-zero, and we haven't written this thing yet, like an equivalent of this thing yet. So that's an independent one. Plus say gamma 2 omega 3 wedge omega 1, that's one. So omega 2 wedge omega 3 and omega 3 wedge omega 1, those are independent because you cannot derive from one from another. Obviously you can try it. And then finally we'll have like that. These are the only possibility, right, for a 2 form to be written. Is that clear?
Yeah.
Okay. Okay. If it is clear enough, then we can proceed. So now, so gamma is a two form, but it's obviously a tensor as well, right? It's a second rank tensor as well. Gamma is a two form, but before that, it's a second rank tensor as well, like 0-2 tensor. All two forms are 0-2 tensors, right?
Yeah.
Okay. So we can try to write this gamma in terms of its like usual direct product terms, like omega wage omega 1 direct product like times omega 2, like that. So let's say if we expand gamma, then it's gamma mu nu, or actually that's going to be a little bit difficult for you. Okay. So if you have a 0-2 tensor, how many independent bases you could have? If you have a 0-2 tensor, in principle, at max, how many independent bases you could have?
In 3D,
In 3D, yes.
3, I think.
It's a 0-2 tensor, remember. Generally, we are not saying that there is an antisymmetry property. So, like for 0-2 tensor, this basis is possible, right? This thing is possible pretty much. There could be
Yeah.
something like that. Then you could have this thing as well. And it's not necessary that actually they are not independent, like they are not dependent at all. So in principle, this thing and this thing are totally independent. These are not wedge product. These are like just direct products. So there are no relations between these two. So if I write the whole thing, a whole array, so how many independent bases we should have?
9.
9, exactly. So like that. Just have patience. Like this part is actually introduction, so it requires a little bit time. But when we get there, everything will be simpler. So if we just did not have this, like when we tell that when you had our gamma to be two form, then it's antisymmetric and we expanded like this. But before that, it's a 0-2 tensor. So why not try to expand like this as well? So let's write our gamma like this. Gamma is a tensor, which is like gamma 1 times this thing plus gamma 1 2 times that thing plus gamma 1 3 times that thing plus gamma 2 1 plus gamma 2 2 plus gamma 2 3 plus gamma 3 1 plus gamma 3 2 gamma 3 3, right? A generic 0-2 tensor could be written like this. Is there any confusion about that? So we could just have some arbitrary components, right?
Yeah.
it's like vectors. So as when we had like vector like basis vectors e1, e2, e3, and if we had an arbitrary vector, we were always able to like write v in terms of basis. So this is like that. So now, if gamma has specific symmetry properties, some of those indices, some of those components, they do not appear. Can you tell me which one? Like, is gamma is a two form, then some of the components should not appear. Which are those? Okay, if it's difficult, then let's expand this object. So if you expand this, we can have actually two things out of it. One is here, like gamma 1, sorry, not here, actually it's 2, 3. So okay, let's start with the last one, that would be easier actually. So we have like gamma 3, like I'm writing down the last term. I'm writing down the last term first. So that's actually gamma 3 times omega 1 times omega 2, and then minus, hello, then minus again gamma 3 omega 2 times omega 1, right? Hello.
Yeah.
Okay, now let's write this term. Where should it go? So 3, 1. So there should be a corresponding term over there, like
Bottom left. Yeah.
yes. So it's what's the component name did I have? Like
Gamma 2.
Omega 2. Okay, great. So omega 2. So then gamma 2, then omega
3 times 1.
yes,
Omega 1.
omega 3 times omega 1, right? Okay, then we should have the opposite one as well. So negative gamma 2 omega 1 times omega 3, right?
Yeah.
So now the first one, this thing. So where should it fall? It's basically like
Top left.
top
Left.
left. This one?
Yeah.
No, there
Oh,
are
no. Sorry. It
two
will be.
parts. So you're looking for omega 2 times omega 3. So this corresponding corresponding to this thing actually. So we should write here, right? So plus gamma 1 omega 2 times the omega 3, and then negative of that term. So that should come over there. So negative gamma 1 omega 3 times it's 3. Yeah, it's 3 times omega 2, like that. And we do not have like this part, and that part. So tell me then, which of those gamma 1 1 gamma 1 2 gamma 1 2, which of those gamma components are 0 then, if gamma is a 2 form?
Uh, 1 1, 2 2, and 3 3.
Yes, this thing has to be 0, right? This thing has to be 0. This thing has to be 0. For a 2 form. Okay. And what else?
These gamma 1 3 and gamma 2 1, gamma 3 1 will be negative of each other.
Okay, so this thing uh, should be equal to that thing, right? So gamma 3 should be equal to gamma 1 2, as you can see,
Yeah.
right? We are
Yeah.
comparing, and again this thing has to equal to that thing, right? So gamma negative gamma 3 should be equal to gamma 2 1, right?
Yeah.
And you can show like from any of those components. So if you have gamma ij, some for some I, for some j, then it must be negative of gamma ji. So the component of a two form is also antisymmetric, and that has to be, otherwise it won't work, right? Like
Yeah.
it's an antisymmetric tensor. Okay, now we do not usually write our three forms or two forms like this. We usually do not write like that. So what I mean is, two forms are 0 2 tensors, so they should have components with 2 index, not 1, right?
Yeah.
So that's why we usually write, for any tensor we usually try to write like this.
Yeah.
For a two form, before going before it is even a two form, we have one thing, that two form is a 0 2 tensor. So any gamma which is a, say it's a two form, we are saying we can write it as gamma mu nu omega mu times omega nu, right? We
Yeah.
can write that without any problem. But what should those components be when we try to write something here with 2 index? So something mu nu, but or like kappa lambda, but here we use, instead of detect product, we use wedge product, because we know there is an antisymmetry. So that's our goal to find. Okay, so now as we already know that we can we were able to write our gamma like this, and if we replace with appropriate component value, then what happens? So gamma 3 should be replaced with what from the above expression here?
Gamma 1 2.
Gamma 1 2, and minus 3 should be replaced with
Gamma 2 1.
gamma 2 1, and so on. So basically we should have some structure like this whole thing, except we should not have this term, that term, and that term, right?
Yeah.
So now now if we want to, instead of doing that, like instead of writing in terms of like considering it's a 0 2 tensor, we just write in terms of basis with wedge products. Then we might assume like gamma has like, say some components big gamma, mu nu, then we have like omega mu wedge omega nu. So all we are trying to find the relation between, like we wrote the same gamma in terms of like this thing as well. So we are trying to find this big gamma, that's all.
Yeah.
So it's going to be a little bit difficult, because when we expand that, it's going to be something really horrible. It's really long thing. Okay, let's do this, because we are going to do this thing just for once, not again. So if we expand this thing with its like mu is summed over 1 up to 3 and mu is summed over 1 up to 3, what should we get? We should get like gamma 1 1 omega 1 wedge omega 1 plus gamma 1 2 omega 1 wedge omega 2 plus gamma 1 3 omega 1 wedge omega 3, like that, right? Then plus gamma 2 1 omega 2 wedge omega 1 plus gamma 2 2 omega 1 wedge omega 2 wedge omega 2 plus, actually let's not write everything, we know what's going to happen. So obviously these components, they should be 0, right? No doubt about it. Or we do not even worry about those gamma 1 1 because it's this, due to this wedge product, that term vanishes, right? So let's erase this.
Yeah.
It's not there anymore. Okay, now what? Now what should be like gamma 1 2? So if you expand this term and that term, you should get similar. And from other terms, you do not get any of this term. Do you know what I mean? Like, if you expand omega, like these two components are dependent. These two bases are dependent. Like omega 1 wedge omega 2 is equals to negative of that thing. That's why. So if you expand these two only, then let's see what happens. So if you expand gamma 1 2 omega 1 times omega 2 minus gamma 1 2 omega 2 times omega 1, right? And then if you expand this one, you get gamma 1 2 omega 2 times omega 1, and then gamma 1 2 2 1 I should write omega 1 times omega 2, right? Like that. So this thing and that thing are same, like they have same basis system. So you can factor out to have gamma 1 2 minus gamma 2 1, right? Then you have like omega 1 times omega 2, and then you have like plus gamma 2 1 minus gamma 1 2, then you have omega 2 times omega 1 2, right? So now we can compare, we can do this thing for pairwise, like there are other components, but we just need to see these two things only, then we'll understand what's happening. So if we compare, so gamma has like, when basis like omega 1 times omega 2, what is the component? It's a small gamma, right? It has a small, this thing has to be small gamma 1 2, and this thing has to be small gamma 2 1, just like that. Now we can solve for big gamma, right? Out of this, solve for like using these two relation, like gamma 1 2 minus gamma 2 1 is equals to small gamma 1 2, and this thing as well. So solve for this one, like gamma 1 2, big gamma 1 2. Can you solve it?
Yeah. It will be gamma 1 2 minus small gamma 1 2 minus small gamma 2 1.
Yes, small gamma 1 2 minus small gamma 2 1, exactly. I think so, yes. Okay, What about gamma 2, 1?
Which will be the opposite. That means gamma 2, 1 minus gamma 1, 2.
It should be gamma
Gamma 2, 1 minus gamma 1, 2.
gamma 1, 2. But we have already seen that gamma 1, 2 is small gamma 1, 2 is the opposite of like negative of a small gamma 2, 1, right? Like you can switch these two indices as well.
Yeah.
That gives you, if you switch these two indices, that gives you a minus sign over here that becomes plus. So it becomes twice gamma 1, 2.
Yeah.
And if you do the same thing here, it just becomes twice gamma 2, 1, like that. So where big gamma is written as these are the components